My name is Alan Athanov and my work is about fragile image watermarking based on convolution neural network. Currently, there are many neural networks able to embed robust digital watermarks into images with the aim of copyright protection. However, in some situations, it is useful not only to save the embedded information in the image, but also to detect the distortion. The aim of our work is to modify the neural network for embedding robust watermarks from the paper Convolution Neural Network-Based Digital Image Watermarking, adaptive to the resolution of image and watermark, to allow embedding a watermark that is robust to one group of attacks and non-robust to another. The original training scheme consists of two parts, an embedded network and an extraction network. In the first step, the image and the watermark are preprocessed, converting them to the same size. Then they are concatenated and passed through the several convolution layers of the embedded network, at the output of which we get an image with embedded watermark. Next, we simulate the attack, and the attacked image is passed to the extraction network, the output of which we get the watermark. For training, we use two loss functions, which are linear combinations of the mean-square error between the input and output images and the average absolute error between the embedded and extracted watermarks. To improve the robustness, we used several pixel value change attacks and geometric attacks. The whole list of attacks with their parameters and their probability of occurrence during training are presented in the table. To make the network semi-fragile, the attacks have been divided into two groups. For the group of attacks that are robust, the bit error rate should tend to 0, and for the group of attacks that should not be robust, the bit error rate should tend to 50%. The second group of attacks includes Gaussian average and median filtering, and as they all affect the image quality. And the second group includes all other attacks. Throughout the research, over 30 versions of semi-fragile watermarking system were tested, all based on the original network. These versions differed in the following aspects, like various choices for the list of attacks used for neural network training, different proportions of attack frequencies during network training, various proportions for loss functions, diverse implementations of attack simulation procedures during network training, and various configurations of the network architecture. Here are examples of the four most successful modifications. The first two of them are based on the exclusion of Gaussian average and median filters, while in version 1.1 the original architecture was preserved, and in version 1.2 another convolution layers was added. The second two modifications are based on changing the loss functions and the frequency of occurrence of attacks. To train the network on attacks that should not be resistant to, we removed the second term from the embedding loss function, which is responsible for quality of watermark embedding, and added the shift coefficient k, which varies for each attack, and the attack intensity to extraction loss function. Moreover, for version 2.1, we increased the frequency of occurrence of Gaussian filter by 2 times, and decreased the frequency of occurrence of average and median filtering by 2 times. While for version 2.2, the frequency of occurrence of attacks has not changed. The slide shows examples of work for all considered versions. namely images before and after watermark embedding and high contrast difference field. In the experimental study, the version 2.1 network showed the best results in terms of image quality and watermark extraction with no distortions. The version 1.2 of the network has the best average attack resistance. However, the versions 1.1 and 2.1 outperform it in some attacks. The version of network 1.1 has the best watermark fragility values, but the versions 2.1 and 2.2 also have advantages. In conclusion, the technique presented in this paper for embedding semi-fragile digital watermarks in images using convolution neural networks exhibits high efficiency in copyright protection, image authentication, and detection of selected types of attacks. When comparing the four considered semi-fragile watermarking networks, it becomes evident that each version has its unique advantages and disadvantages. However, in general, version 1.1 can be distinguished as the preferred option in terms of robustness fragility, while version 2.1 outperforms the others in the visual quality of protected images. Thank you for your attention.